and then hand over to you. Welcome, Islam.
Right. Thank you so much. So today, I'm going to give you a brief overview of how the field of connectomics is being revolutionized by generative AI, including also federated learning and other perspectives, which will revolve around holistic learning. So let's get started right away. So AI has revolutionized healthcare and medicine, as we all know. So there are big trends. So here in the Forbes, there has been the publication of an article showing the 10 biggest trends revolutionizing healthcare in 2024. And these include primarily personalized medicine and generative AI in healthcare. Now, on the other side, I want you guys to look at the rate of growth of generative AI worldwide. So this is, the market size of Gen AI up to 2025, and this is the projection in the coming 5 years up to 2030, sorry. So here you can see that the US is actually, the US and also worldwide, we have like an exponential growth. And if you look at the Africas, the growth rate is very minimal, although it is catching up, but the pace is much, much slower. So what does this graph tell us? It tells us that generative AI is actually invading a lot of fields. And here we're going to focus primarily on healthcare and how can we leverage it to solve critical problems, including, for example, the problem of discrepancy in the deployment, the use, the development of AI across continents. Yeah. So there are three trends in the AI-powered healthcare revolution. So the first one, which I believe like we were amongst the very first, not the first, to pioneer the field of generative AI with application to network neuroscience. So I'm going to show you today the early works, a few of the early works. So I'm not covering recent research works because we have a lot of projects and publications. So I'm just going to give you 3 cases to cover each of those. So first, generating the multidimensional brain network. When I say brains here, we primarily focus on the brain connectome or the brain graph. Generating population brain templates. And in the second part, I'm going to cover federated learning, how we leverage federated learning to generate the future of the brain from multi-source data, large-scale data sets, ideally. And then this part, I'm not sure if I have time to cover it because I have so many slides, so probably skip it. But yes, so it's basically leveraging federated learning for heterogeneous diagnostic tasks. And the last part is a sneak peek into a field that I don't believe it exists right now. It's a very old concept that I want to revive it. So I'm going to give you a few ideas to think about before I wrap up the talk. Okay. So it's related to holistic learning, the future of how can we shape a future that is more inclusive and holistic in terms of AI application and development in connectomics and healthcare in general, not medicine. Yeah. So here we're going to start first with the generative learning problem. So how can we generate multi-dimensional brain networks? How we leverage AI to do brain generation? So in this here in this example, we can see the beautiful brain matrix. I think all of you know what it is. So this is basically the adjacency matrix of a brain network/graph. So we have different regions in the brain, and the weight here represents or quantifies the interaction between pairs of regions. Okay, rows and columns here. So what is interesting, if we learn how to read this matrix, how to depict the patterns in this matrix, we can design algorithms that can predict if you're feeling sad, your brain states, like mental states, happy, inspired, well, hopefully. Also eavesdrop on your decision processes and your love life. And there has been a lot of papers that actually show this. From the matrix, we can predict these states. Yeah. So now this is another beautiful matrix. It represents a morphological brain connectome. So we were also amongst the first to generate or to propose the concept of brain morphological networks before the emergence of the morphology similarity network. So this is not based on a similarity between different measures. Actually, we take a single measure. The first paper was published back in 2018. Yeah, so basically here we look at the cortical surface, one hemisphere, we parcellate it into different regions of interest, and we have, for example, the thickness, the average thickness of region A, region B, and we calculate the difference between them or the distance between them. So it's measure-based. And what we notice here, this is a perfectly healthy brain of a baby, a newborn baby, and here, the matrix basically reconstructed after 3 months or acquired after 3 months. So you can see the dramatic changes that the brain morphological brain connectivity related to thickness that like it undergoes basically a lot of changes. Okay. So trying to understand how the brain evolves, the connectome evolves over time, this beautiful matrix is a long life journey from the cradle to the grave. So if we look here, we see another matrix of a healthy subject, so a 75-year-old subject. And now if we look at the other matrix right here, so this matrix has been diagnosed with mild cognitive impairment. It's a functional connectivity matrix, and we can see also the changes in the connectivity patterns between these two subjects. So basically, what we try to do is, of course, develop algorithms that help us interpret these matrices, because if you just look at them, it's hard to identify the changes, right? So we want to automate that. We want to identify the most important changes, and this will eventually, maybe in the future, help administer connectivity targeted treatments with the development of technology in medicine and connectomics. So let's see about that. Yeah. So now the question is that you guys may ask, I've been showing you matrices. However, the key question here is that how do we actually get the matrix? And for each matrix, for every brain network or every brain matrix, we need an image. All right. So this figure, this world map, basically plot has been published in the Lancet Oncology in 2021. And here, what it shows is the estimates of the number of MRI units per million inhabitants. And what you guys notice is that there is a big gap between the north and the south. So there are so many countries that have only a single to 2 to 3 scanners, MRI scanners in the whole country. So ideally, we would increase, the access to these MRI machines. So the mainstream solutions that were proposed in this paper is to increase access to this technology to train people. However, I would say this is time consuming. It is also costly. So the idea that we had is that instead of acquiring the data, how about we generate the data? So we're not solving this problem, by the way, because, maybe with EEG we can. But yeah, so I'm not solving it fully, but we're trying to at least minimize the extra time and the extra money that we may spend acquiring future sequences, future MRIs, or cross-modality MRIs. So that's a first step, a first milestone towards solving this problem or bridging this gap. Yeah? All right, so now here is a question for you. Can we diagnose early and better with minimal resources, which means with limited data and at lower costs? Okay, so first, imagine we have a data here, an input data. We call it X. So this data is affordable to acquire. It is accessible. It could have a low to middle quality. So we don't need to have a very high quality of the input data X. And our goal is to generate X hat. So X hat would be costly to acquire and accessible, let's say in many countries, of high quality. This is the ideal scenario. We're not fully solving it, but as I said, it's one step towards this goal. Right. So the goal here is to learn a mapping function or to design an intelligent algorithm, a deep learning. For example, graph neural networks, I've been using them over the past few years because they're very well suited for connectomic data. And yeah, so the goal is to design a mapping that takes x, f of x, and outputs x hat. So the idea here is that starting from minimal data, we get high quality data, but actually there is no real data there, right? So we're generating it. So we actually had a lot of papers published since 20, I would say like 19 to last week, actually. So this has not been updated. But yeah, so anyway, so we called this field predictive learning years ago. So I suggested or like I proposed this workshop on predictive intelligence in medicine years ago in 2018 in conjunction with MICAI conference, which is the top conference in AI and medical imaging. And now, like we have been basically predicting data from data, right? So now we call it generative learning, but the terminology is the same. So here, what we have the input data is a T1 weighted MRI. So we derive the morphological connectome from T1 weighted. So there are different ways of doing that. But yeah, so let's say you have your own image processing pipeline that will derive the connectome from the T1 weighted. And then from this morphological connectome, now we want to generate its counterpart across different modalities. So from the morphology, we derive the function, the diffusion base, without the need of actually acquiring diffusion sequences or resting state functional MRI. So we didn't work on task-based. These models are still very reductionist, but they work quite well as a starting point, I would say. So the other dimension of this space is the resolution. So let's say, but what I mean by resolution is the number of nodes or the size of the matrix. So here we have 6 by 6, right? 6 nodes. So the idea is actually it may be costly to do parcellations at finer scales. It takes time. We may need some manual kind of, verification, right? So or evaluation. So we circumvent also the need of costly image processing techniques and pipelines, and we directly generate the connectome at larger scales / resolutions. Yeah. And the third dimension is time. So it's easy. So give it a snapshot of your brain at time point T. We predict its evolution over months, years. It depends on the data that we have. So this is a fully three-dimensional, multi-dimensional generative space where we given a single input, a single matrix, and we span all other matrices across the 3 dimensions, okay? Of course, you can add other things like states, right? So whether you have like a particular diseases, like healthiness, like a spectrum of healthiness, if you can discretize that, and you can have a fully multidimensional space of generated connectomes, yeah? So now, this summarizes conceptually in an abstract way what we're trying to solve for the first task, which is a single graph generation or prediction. So we have a source graph, and the goal is to learn a mapping function or I would say, like a deep learning model that predicts a target graph from a source one. So it's a one-to-one prediction. For the multi-graph prediction, we have the same parcellation, the same ROIs, but we generate multiple graphs at the same time across domains. For example, from morphological graph here network, we predict or generate the structural connectome, diffusion base, and functional and other type of morphological maybe graphs or hybrid ones. So yeah. So the second axis here is resolution. So from a low resolution graph of the brain, the connectome, we generate a larger matrix. Actually, I organized 2 competitions around this. We were the first to introduce the concept of graph super resolution. So even in graph theory. So previously, the concept of super resolving data applied to primarily, or I would say like fundamentally images, right? And videos. You want to get your images better, your videos higher resolution at higher resolutions. But what is the point of actually super resolving a graph? So this is a perfect problem for the brain network because instead, as I said before, instead of like using sophisticated and costly image processing pipelines to get finer parcellations of the whole brain. We take a small parcellation, right, like just a few region, let's say, I don't know, like for example, 30, and we predict a 300 by 300 or even more. Okay, so it depends on the data. So the applications is data focused, but this is very generic. Yeah. So here also you can predict in a completely different domain. So which means from the morphological network, you can predict the functional at a different resolution. Yeah. So the third dimension of this space is the time. So given a time, an observation, an observed network at time t0, we aim basically to predict it at follow-up time points and generate the full evolution trajectory, a dynamic trajectory of this network or connectome. So now the last concept that I want to also introduce, which is a concept that we also pioneered, the concept of a connectional brain template. So we all know that we have the concept of an atlas or a template for images. So you have different atlases that you register your images to bring them to the same space, and then you do segmentation, you build the connectome. So these are very well known in medical imaging, I would say. But the concept of a template, a connectional template, an atlas for a set of graphs, for a population of graphs, have never been explored. So we basically came up with this concept of brain templates, and I will show you some exciting results in a bit. It's still a niche, I would say, research field. But it has a lot of promises. So the idea here basically is that we have a single subject. So this subject is an individual, like my brain, for example. I have different views, different connectomic representations of my brain, my functional connectivity, structural, morphological. At the same, of course, here we have the same scale. Actually, we tackled the problem across scales, but as I said, I'm going to just stick to this. So let's say for now, hypothetically, we hypothesize we have the same parcellations, the same resolution. We're just depicting different edge types, okay? So multi-type data, multimodal data. And we collect that for many subjects. So we have, for example, N subjects. So we have a population of multimodal brain networks or multi-view brain networks that we want to integrate into a single template. So a single matrix, which basically depicts the fingerprint of this population, okay? So now, okay, so you may ask me, what is the point of all of this? So the point is, once we get the generated data across domains, across time, maybe we can also use this at some point, this template to guide our diagnosis or learning. But the goal is to use the generated data along with the source one to do some augmentation and improve multimodal biomarker discovery without the need of acquiring the data, because now we're generating the functional and other types of connectivity. So we can do multimodal biomarker discovery if we trust the data enough, of course. And then you can do diagnosis. You can do a lot of things, right? So basically, you take what you have generated along with the ground truth input, you put it together, and you do your analysis, okay? Cool. So now let's move next. So all these works, actually, all of them are have been accepted to top conferences, workshops, and also published. I don't do journals, but the oral presentations are on YouTube, so you can watch these if you're interested. And there is a review paper that we published 2 years ago. It's called Graph Neural Networks and Network Neuroscience, that covers a lot of the primary works on these on these tasks. Yeah. Great. So also, if you're interested in running these codes, we have demos, GitHub video demos on how to run the code. A lot of them have been, like codes are very tricky, especially when you publish them 5 years ago. So anyways, but yeah, so all our source codes are available. You can, for example, we have a survey on multi-graph integration. Everything is available there. This is for regression using GNN. So yeah, so different codes. So we put everything. All our works are reproducible, inclusive, as we promote open science, and you can check the list of videos here. So now we can get to to see a few real examples. All right, so the first one is cross-resolution prediction or generation. So what is that? As I mentioned, first you have a parcellation of the brain into different regions. So here, for example, this is the input matrix, and we want to learn how to generate high-resolution brain graphs using graph neural network models. So that's our AI model. And the goal is to generate this matrix from this one. So this is just, as I said, we use generally public data sets. We didn't work on private data sets. So we focus primarily on methodology. But I believe with collaborations and with also some local data sets, there is still a whole lot to do and to explore using these methods. Yeah? All right, cool. So this was the first paper that used graph neural networks to generate brain connectivity at higher scale or resolution. So the question here, it's a bit mathy, but I'm going to simplify everything. So how to predict cross-modality or intermodality brain graphs from a base one. So non-isomorphic. So here, basically, we break the isomorphism. We have a fully connected graph, and we break the resolution. So the conventional methods published at the time, they focus on generating brain graphs, like the purple ones here, from the pink ones, the orange ones, I think, 7, whatever. Yeah, so using at the same resolution, right? So what you guys know this, if we go from domain A, from the source domain to the target domain, there's a shift in the distribution. So the existing works at the time did not handle the problem of what we call the domain fracture or shift between the distribution of the morphological connectivity and the functional connectivity. So that's what we try to solve using this our network. Yeah. So the proposed solution aims to solve two challenges. The first one is we basically break the resolution size. So we have two different resolutions, NR by NR2 and then NR prime by NR prime. And we solve the problem of the intermodality shift, right, in terms of distribution. So here we propose Iman GraphNet. So it has two learning blocks, and these are very intuitive. So the first block is an intermodality domain aligner. So we take a set of networks. Let's call these are the connectivity matrices, X1 to N. So we have N training subjects. S is the source domain. And then the goal of this network is to align the distribution of the source, which is the purple one here, like the pink, towards the blue one, which is the target. So as we train the network, we do not change the topology. We only change the distribution of the weights in such a way that it aligns with the distribution of the target. So why this is important? Because imagine if you have somebody, I don't know, like let's say you have completely two different spaces, right? So you have somebody on Earth and somebody on Mars, and you want to do some calculation. You want to do some comparison of the local dynamics of me walking on Earth and somebody else treading Mars, let's say, right? So the comparison will not be straightforward unless you really bring those to the same space, right? So the first thing here is that we bridge the gap between the spaces by aligning the distributions, right? And now we can super resolve or do some, advanced, I would say, analysis in the same space. So basically, bridging the gap in the distribution allows us to solve the problem better because now they are proximal. So the generative process should not take a lot of maybe optimization, right? So here, the second block of Iman GraphNet is the non-isomorphic part where we actually do the super resolution. So now we have the aligned source networks, the low resolution networks, these matrices that were aligned as towards the target in terms of distribution. And then we pass them through this GNN model. It's a GCN model. And we use an adversarial learning just to make sure that to regularize. So we use the graph GAN where we make sure that the target, the ground truth is closer to the generated one. All right. So the generated one is closer to the ground truth. Yeah. So here, these are the building components. So primarily like a GCN layer, dropout, batch normalization. So these are conventional components of deep learning. It's very simple. And the results were very interesting. So we tried this on the SLIM dataset, it's a public dataset. So we had 150 morphological connectomes parcellated at 35 by 35. And then 150 functional connectomes, 160 by 160. And here are the results. So first, These are the MAE, the mean absolute error between the ground truth matrix and the generated matrix in the high resolution domain. Okay, so just the difference between the matrices and you average across your testing samples. All right, so of course we use cross-validation here to evaluate our model. So if you look at the MAE, simple, right? Just between two matrices in terms of edge weights. Now we have closeness centrality. So we see how good is our methodology in preserving topology. We have BC, between a centrality, and eigenvector centrality. So we picked three topological measures, and we see the same trend. So basically, when you take Iman GraphNet without any alignment, you have the largest error here, right? The pink ones. And then when you do some statistical alignment, it's a manual alignment. So we do this is what we call an ablated version. We take out completely the first block. We only train the second one. So we remove the alignment, but we pre-align the data statistically. So we shift the means and the standard deviations. We bring them to the same statistical distribution. And you can see with alignment, even statistical alignment, we do have some improvement, right? So the error drops. Now, we had also some technical innovations, like we proposed optimization losses. So I'm not going to cover them, but we had two of them, one with topological loss, one a Pearson correlation loss. And when we took these out, these are without the ablated version of Iman GraphNet, we can see, now a good improvement also in terms of decreasing the error. And this is our model. And when used two-tailed pair t-test, the outperformance is statistically significant here. So yeah, and then we did some clinical introspection by depicting the top 5 connectivities, and we saw we compare the ground truth versus the predicted one. But yeah, so if you guys feel free to have a look at the paper. The full 20-minute video is available, also explaining all the mathematical side and the results in detail. Also the GitHub repo of the code. Now, the second point is generating population brain templates. So I explained why we need templates. Or atlases. We also call them connectional brain atlases because they look at the connectivity. It's not just an image atlas. So here the problem statement goes like this. So basically we want to integrate a population of multi-view brain networks to estimate this connectional brain template, right? So we have different subjects. Each subject is represented by different matrices. We hypothesize that they have the same parcellation, which means they are in correspondence. So the region J here is the same across all these matrices. So this matrix right here represents, for example, functional, connectivity, morphological, etc. And our goal is to actually learn how to integrate this. So feed this into a graph neural network that will output a single matrix, okay, which we call it the connectional brain template, CBT. Hopefully, it will discover the fingerprint, the connectional fingerprint of this population. So CBTs are powerful tools for group comparison studies and discovering what we call the integral signature of particular disorder or abnormality or anomaly in the population. So let me expand more a little bit on this. So what is our rationale? First, we start with, let's say, a healthy population. So we have a population of healthy subjects. So we know that each brain network is a fingerprint, individual fingerprint. There are so many publications on that. So we must have some shared connectivity patterns because we're all like we have similarities, right, in terms of cognition, function, etc., structure, right? So there should be some shared patterns, connectivity patterns, like this triad right here. And some variable connectivity. Now, the key question here, how we distinguish between what is typically variable, and atypically variable, right? So if you look at the distance between these two, you may think it's abnormal, it's atypical, right? So this connection has become thicker here, or thinner here, maybe it's an anomaly in the network, right? So the idea of using a CBT in a population, a healthy population, is to actually regularize or normalize this typical variability and find a shared pattern. So if we learn a good CBT, we will be able to get maybe a connectome that looks like this. And if we apply the same algorithm to another population, a disordered CBT, we'll get this connectome. Now, if we compare, we can easily identify the connection with the highest difference, right? And that enables us to identify connectional biomarkers just by comparing the connectome and the matrices. So once we have these fingerprints, these CBTs of different populations across different disorders, we can span the landscape of, I would say, neurological brain disorders and other types of diseases, right? By mapping these CBTs in the space and comparing them simply without resorting to doing extensive analysis. Because if this matrix is representative of the population, what is normally there, typically there, right? And this one also depicts what is atypical. So by simply comparing them, you can see that this is the most discriminative connection here. So that's why CBTs are powerful. Now, you may think about this problem as an averaging problem, but I'll tell you why averaging doesn't work, okay? So a good CBT will occupy the center of a population, right? So it is well-centered and it is discriminative, which means it captures what is unique and, about that population, the common traits or the common connectivity patterns. So we can depict them once we integrate them into this matrix. So the first work actually was selected for oral it was an early accept at MICAI 2020 conference. As I mentioned, so this is the top conference in AI and medical imaging. And we designed the deep graph normalizer. So it's a geometric deep learning approach for estimating connectional brain templates from different populations, right? So the idea here is the DGN solution, which is state of the art, by the way. Well, relatively, still state of the art, very close. We had some variations of the model, but they're still quite close to DGN. So we first do the node embedding. So let me explain what we do here. It's very simple. We have a tensor of matrices. So we have 3 connectomes here, one representing one single individual. We pass it through the network. And the goal is to get what we call a representation or an embedding learned for each node. So for each node or for each ROI brain region, anatomical brain region, we learn how to represent it by a set of digits, numbers, okay? So we have V1 for ROI1, V3, ROI3, etc. So the goal of this node embedding network or GCN is to actually learn these embeddings. If these embeddings are very well learned, now we can take, for example, the difference between them or the Pearson correlation if we're working on functional connectivity, and we can derive the connectivity, the edge weight, right, by calculating a similarity measure or applying a particular metric or measure to these two embeddings, like, for example, V1 and V4, yeah? So then we get this CS. So the CS is actually a connectivity matrix for subject S. Now, the key question is, how do we actually make sure that this CS is now centered, right? So it needs to be centered, right? So imagine a cloud of points. And the cloud of points, you want to create a center of that cloud of points. So ideally, you would bring each subject closer to a center, right? The center is unknown to us. So that's what we call the CBT. It's the center of the cluster. So the key idea here is lies in this loss function that we propose, which we call the subject normalization loss. So in a nutshell, what we're trying to do, we look at the distance between the CS, what is learned. So this is something that we are learning. So we're currently updating during the optimization. And we have a set of training subjects. These are the tensors of subjects I across for view V, right? So subject, for example, 1, and we have the second view 2, etc. So we loop over all views, all subjects, right? And then we try to minimize the distance between CS and all other subjects. So the goal is to minimize the distance between this guy, the CBT, and all other subjects, yeah? So if we do that, then we are sure that CS will be minimally close to all of these training samples, so which means our matrices, which means it is centered. So once we do that, so I call this a cloud collapse strategy. So you have a bunch of points every time through the optimization, you're bringing each one closer to a center until everybody is close to each other. So you collapse a large cloud of points to a single sub space where everybody is close. And now you can easily use an average or you take the medium, element-wise medium of all these subjects. So we repeat this for every single training sample in the population, each one of those. And we get a C1 for first subject, C2, etc. And then once these guys are close, now we can easily average. So the problem is that why we didn't go for averaging? Actually, the very first paper that was published, it dated back to, I think, 2000, if I'm not right, yeah, 2000, I think, and 18 or even earlier. So the paper was using machine learning, not graph neural networks, so conventional machine learning methodologies to get a CBT. And we actually outperformed the performance of that paper using GNS because they're much more powerful. And the original paper compared against average, and averages can be easily biased to towards outliers, which means if you have a few points lying outside of your cloud or far away from the cluster, right, they will bias your average. So that's why the average has the worst error ever. So yeah. So now, yeah, so we have done, we extended this into full journal paper in the medical image analysis journal. So we had an advanced, we actually upgraded the DGN. We added a few topological contributions, and we used different data sets, Alzheimer's disease, late mild cognitive impairment, and normal controls versus autistic spectrum disorder subjects. We had 4 morphological views here, 6 morphological views, different subjects. But yeah, so we had 40 comparison in the paper, and across all of those, it outperformed net norm, which was the original paper. And then, yeah, so we also showed that we can, by easily comparing the two matrices, we can identify discriminative connections or biomarkers. And we compared them with a completely double-blind study where we ran machine learning algorithms to identify the biomarkers, and we had a very high overlap. So an overlap between a method that is learnable and a method that just compares two matrices, the output, okay? So yeah, so you feel free to have a look at this if you're interested. So I'm just going to go quickly now because we don't have a lot of time left. But yeah, so here you can see the key biomarkers we discovered for this, and they were replicated, or like they were in line with the literature, also for AD and LMCI. And yeah, so we also my former PhD student Nada, she wrote a comparative survey of including all methods that do multi-graph integration, and these are generic methods. You can apply them to any data as long as it fits this framework. And what we noticed is that DGN actually outperformed all of them, including SNF, which is a Nature paper published in 2014 for integrating graphs or networks. So yeah, so this is it has like the best results across, I think, 8 data sets, and I don't know like how many measures we use. So all these have been evaluated. We used all these evaluation measures of hubness behavior, segregation, integration, global behavior, level similarity, etc. And the templates that we generated were highly reliable across all these evaluation measures. Yeah. Okay, so yeah, the codes are also available and the plots that we generated. So everything is available on GitHub. Now, we get to the second part, which is federated learning. So in this federated learning, I'm going to cover only one part, which is federate to generate the future of the brain. So I'm going to talk about generative neuroscience across time, temporal. So the goal here basically is to learn how to generate brain networks across time. So we had a lot of studies before that, but today I want to cover the advanced concept of federation because I do believe it could be revolutionizing, and it can also help decrease the gap between the North and the South in terms of connectomics data sets and generation. Yeah, so here in this example, the goal is basically given a brain connectome observed at time point T1, we want to predict the evolution of the network, so the whole trajectory, and we would have specific particular follow-up time points. So what is federated learning? So here is a question for you before I answer that. Can we learn better together without sharing our data? So we know clinical data and connectomic data, imaging data, MRI data is, very valuable. It's not easy to share it across. That comes with a lot of ethical work. So medical data is needs to be private, preserved, unless, you made it public according to some, criteria and protocols. But in hospitals, in local hospitals, like we don't have that. So the data is private. And the goal here is actually to leverage to address this question, to actually learn from the data without accessing the data, which is a very exciting concept. So this is actually the original paper was published in 2017 by McMahon, and he introduced the concept of federated learning. So it's a decentralized framework for training global models without sharing local data sets. Yeah. So what is the idea here? So the first model is called Fed average. So it's very simple. Have a bunch of hospitals. Given a set of hospitals, we have K hospitals here. Each hospital acquires a particular, the same, like a data set for a particular disease. Okay, so we have the same disease here. Let's say, for example, I don't know, Parkinson's disease or dementia, etc. So here we have histopathological images. Just put images here to illustrate the concept. And we use what we have. So each model would train its AI model internally, and then they will share the parameters or the weights of the trained models with a server. So because the trained model, it takes an input X, outputs X hat, right? So this hospital has been trained on its own data. The distribution may vary, right? So if this hospital is here and this hospital is in, I don't know, Tunisia, and this one is in Guatemala, for example, right? So the distribution may vary because maybe the scanning techniques will vary, population, genetics, a lot of other confounders would vary. So the idea here is that each hospital would train its local model, but then this local model somehow, without revealing the data, it has learned on the data. So it somehow encapsulates the data. So the idea is that if we somehow aggregate all these models together, we will get a global knowledge of this particular disease. We will be able to learn from these cohorts without necessarily accessing the data. So we send this to a server. The server averages or aggregates these models and then broadcasts back the average model to these hospitals to continue their learning and their training. So this is a single federation round. A single federation round is like, I'm training my local model. I send it to the server aggregates, it sends me back a global knowledge that will help me improve my local training because now somehow I have access to other parameter weights from other models. And then locally, I am able to generalize better, to diagnose better, okay? So here, what we did is we leveraged this concept. So there has been a recent paper, I think it's published one in Lancet, in the Lancet journal. So it's on new system. It's about the using federated learning to diagnose or screen COVID-19 images, and this has been it's a very nice actually solution because it's low cost and privacy preserving. So they developed what they call a full stack federated learning to train and evaluate machine learning models across 4 UK hospitals groups without centralizing patient data. And the results are very interesting. So this, of course, could be also is something I'm interested in. If you guys are interested, let me know. We have actually published a few other works on template learning using federation. We have a bunch of papers connecting federated learning with connectomics, but it would be nice to actually do this in real time, not just on public data sets. Yeah, cool. So this was a paper published by my former undergrad students. So we got a MICAI workshop paper, and we extended it into IEEE TMI, which is one of the top journals in computer science and medical imaging. So transactions on medical imaging. And the goal of this paper is actually to learn how to predict the trajectory even when you have missing time points, even when you have a single observation to train on. Like, let's say you collected a data for patients, but you only have a single time point. But thanks to the federated learning, you can still predict the whole trajectory. So something that doesn't make sense if you were to use just simple AI models, because you need to train on data to predict the data, okay? So here, even without having the data, you can still predict. So let me explain the concept here quickly. So here what we have a beautiful matrix right here. So this matrix represents the number of hospitals and the number of time points. So what we have four scenarios. So we designed a GNN model, a graph neural network that takes in the brain network at time t and predicts the next time point t plus 1. So that's the output of the network, okay? So we're trying to predict the next time point. Now, how do we do that? This generative network will act differently depending on the scenario. So we have two action points right here, whether it acts as a self-encoder or as a generator. So two actions. So the first action is generate. So whenever the next time point is available, right? So the t plus 1 is available, then it acts as a generator, which means it will learn how to map t to t plus 1, right? So for example, here, the next time point is available, so it will still learn how to map. So when the next time point is missing, like in this case or the last case, right, the fourth case, then it will actually act as a self-encoder, which means it's an identity mapper. So it takes the input and almost copy paste and outputs almost the same thing. So the key question here, you may ask, why would we self-encode, right? Does it make sense to take my brain 5 years ago and to copy paste it into my brain right now? No? So this doesn't make sense, but it will make sense in a bit. So because we have federated learning. So what we have here, as I mentioned, you have different hospitals. So every time, let's say a hospital, H0 here, has all time points. So if I communicate the hospital that has the next time point to this hospital, H2, let's say H2 doesn't have a time point t plus 1, it has 0. So the time point has not been acquired, maybe because of the patient missing the scan or whatever, right? So what happens here, when H2 trains its local model, it doesn't have the data, but it will still hallucinate something. It will generate something. But thanks to the aggregation, because here we designed a smart aggregation algorithm, so we only have we propose an ordering of the hospitals. So those that are richer, which means they have the most complete sequences, will communicate their knowledge to the poorer hospitals until reaching the end of the chain, right? So if you have a lot of acquisitions, you have a full sequence 1, 1, 1 to 1, right? Then we will aggregate from the guys who have the information and communicate that to the guys who do not have the information. So what happens is that these smart, intelligent machines will just learn so fast, and they will learn how to generate something really plausible without accessing the data because of the intelligent communication between them. Okay, so somehow the hospital that doesn't have the data now is able to predict something very reliable without training, while training on nothing, thanks to this aggregation. Okay, so that's the principle. Feel free to read the paper. You can ask me more if you want, but I just want you, I wanted to give you the gist of it. So we used cross-validation, actually one-fold, like we split the data into 5 random sets, one for testing, and 4 we distributed them against the 4 across the 4 hospitals, and we shuffled that multiple times, and we got the results. So we compared against 4D GNN, which is without federation. This one for 4D Fed GNN with federation, and the plus, and we have another version which is the plus plus. So and you guys can see here, like with the smart ordering, we have the lowest error in terms of predicting time point T1 from T0. So this we look at the ground truth and the prediction, and we calculate the MAE, mean absolute error, and you can see that federated learning actually decreases a lot the error. And when we have a smart aggregation method with ordering based on completeness of data, that improves further. Same for the second time point. So we have the same trend, always decreasing. Yeah, cool. So if you want to learn more, you can watch the full video on federated time-dependent GNN, and the code is also available. Okay, so now I have a few minutes to wrap this up. Perfect timing. So I will not cover the federated federation of heterogeneous diagnostic tasks, but I want to just, towards the very end of this talk, I want to bring your attention to a few points here and there. I'm not fully fleshing out the landscape for you. I'm just giving you the dots, guys, and it's up to you to connect them the way you want, okay? Cool. So let's not forget that in the age of AI, medicine, used to be practiced in a different way. So I just want to question the way medicine has evolved, the way our understanding of neuroscience has evolved in neurological diseases. So Avicenna here, he was amongst the first to look at the treatment of a disease not from a purely medical treatment, pharma focused, I would say, business, right, or endeavor. So here we look at the disease from the patient perspective. So the physician should not treat the disease, but the patient who is suffering from it. And sometimes, like nowadays, I think we're lacking such connections, even in conventional hospitals, let alone when you have an AI doctor diagnosing you one day or app, and particularly for very conventional things, like simple things like 1 + 1 = 2, not complicated cases, right? So, what I wanted to bring to your attention here is that maybe we need a more holistic way of looking at diseases, disorders, connectomics. I'm not aware of any research in this regard. I know there is mental health. I know there, if you are aware, please let me know. Just ping me, like email me papers. I'm happy to have a look and I would be grateful. So, what I wanted to highlight or like bring to your attention is that maybe the way that we are actually treating patients and like conducting research is lacking something, and it's lacking something really fundamental. So why I'm saying that? Because as a research scientist, I'm not a doctor, I'm a computer scientist, but I have been working in the field of medical imaging for a long time, and also particularly in network neuroscience. And I came across this book a few months ago, and I was like, okay, I was never intrigued to actually look at how diseases evolve, right, across time, across populations, and why there's an increase. So we are supposed to be in the age of technology, in the age where we have power and money and all these exciting things happening, right? Like somehow, in a very naive way, I should probably ask somebody who's in social sciences, right? I couldn't understand why we have this growth, right? So if we are evolving as a species, why the diseases are not decreasing, why we are not, like in a better shape, right? So I'm questioning the whole system, the whole view of this, of medicine, of mental health, of well-being. And what you guys see here, like all cancers, like for women, these are trans cancer incidents, until 2011. And they're all increasing almost across countries, right, with variability there, but they're all constantly increasing. So in this paper, they say the rise and fall is, the usual time pattern in which diseases afflict human populations might have a deeper explanation. So why have, in the course of human history, so many diseases emerge? Why have, on the other hand, and with shorter or longer delay, most of these diseases become less common again, or at least become less lethal? And I believe now, in the age of AI, in the age of data, we can answer these questions, right? If we have access to all these data sets, or somehow with federated learning, we can access, knowledge from these data sets, we will be able to track the evolution of these diseases and understand why we have the rise, why we have the fall. And I think in the coming years, I believe if we start tracking this properly, I know in other fields like computer vision and social media, it's a lot easier because medical data is highly sensitive. But if we can build these AI agents and these AI systems that can learn from these data across continents and across cities and neighborhoods, right? Then we can try to understand why we have these patterns and hopefully get into developing more preventive, I would say, solutions rather than treatments. Yeah. So we need a more holistic approach. Are we asking the right questions and looking at the right data? So that's something I always ask myself, but I'm not sure I think it's important to just ask these questions until you get the answer. Another thing I wanted to bring to your attention is the generative AI. So I am using generative AI. I'm keen on generative AI. I know it has an amazing potential in medicine and beyond, particularly in connectomics. However, generative AI is actually really costly. So you can see here the volume of data information consumed from 2010 to 2025. And this is a 10 to the power of 21 bytes. It's huge. You cannot imagine that number in terms of zettabytes. So these numbers, I'm not able to even imagine that. So it's devouring a lot of servers. It's devouring a lot of electricity, a lot of power, right? Just to train these, to store these data sets, right? And in terms of environmental pollution, like how much AI, generative AI models actually generate, you guys can see here, this is the CO2 equivalence emissions by AI models 2024 in tons, and GPT is acing it, right? So this is just 5 years ago. Now I don't know where it is. So what concerns me is sometimes we get really hyped up and excited about so many amazing endeavors. There's a lot of funding that goes into that. I'm amongst the ones who chases that too. But at the same time, I'm asking, are we doing this actually in the right way? And the picture is completely incomplete because we are not connecting with people from the other side, from humanities, from the social sciences, to actually try to understand the effect of the technologies that we are developing and using to treat people. And these people could be very close to us. Yeah. So just to wrap up, what I presented today is the generative learning, its ability to generate costly medical data from low cost, enable the forecasting of health disease evolution at individual population levels, improve disease diagnosis, hopefully in prognosis, the concept of federated learning, which promotes also low cost and privacy preserving learning from data. So you can learn from different devices across the world, different hospitals, increase AI fairness by learning from diverse data sets, learn better together and without data. So these are our principles from federated learning. And at last, the other side to rethink. So holistic learning, Gen AI, at which cost, and how to enable a more holistic learning and healing of diseases. Yeah. Thank you so much for listening, and I'm happy to take your questions.
Right, thank you, Islem, for a really fascinating talk and some really thought-provoking questions at the end. Okay, so I can hang on. I need to stop the recording. Let me just see where I need to